Right, now we're going to talk about something really exciting, subgroups. You know, we've been filling the box, relations and all sorts of things. In the beginning, it was boring. We filled it. We don't know where it belongs. We filled the box. We've eventually started looking at groups. Things got interesting. Showed you integers, mod n, some other groups. So, you know, we're using stuff out the box. It's getting more exciting. It's getting more exciting. And now the excitement just ramps up because we're going to talk about subgroups. So remember, G is a group if I have the set A and its binary operation with the four properties. There's closure under that binary operation. Associativity holds. Associativity holds for any A, B, and C element of A. We have a unique identity element called E, and then there's a unique inverse for every element, for each element in A. So A contains all its elements, and for every element, the unique element is also there. One of them is the identity element. There's associativity and there's closure. Now imagine I have a subset of A called A prime, a subset of A called A prime, and I have the same binary operation. Now I can create this subgroup of A prime and that same binary operation if these properties hold. If these properties hold for this subset of A, the elements in A, then H will also be a group, and this will be then called a subgroup. That's the definition of a subgroup of G. The definition of the subgroup of G. All these things must hold, though, for that to be so. Remember, I can have two special ones, though. I can say that A inverse contains only the identity element, and I can have that A inverse, is equal to A. And yes, that will make a subgroup of H, but those are called improper subgroups sometimes, and that's not the ones we are after. We are after taking some elements out of A so that it is a proper subset. It can't be an empty set, and not one of these two. And if I have that same binary operation, they've got to be the same, and all four hold, then H is a subgroup. That's our definition. Turns out, though, I actually don't need all four, because there's this following theorem. A non-empty subset H. Now here I just used the A and subset and the subset of A. I'm just going to shift a bit and just call this thing the G and the H both a set and group. I'm going to use the term interchangeably for these. And please just know that it includes the binary operation as well. So I'm going to say a non-empty subset H of a group G is a subgroup of G if and only if the closure property holds. So if A and B are an element of H, then AB, and that should be A with its binary operation there. I've just, most of the time we just leave it out as an element of H. And every element of H has a unique inverse in H. So if A is an element of H, it implies that A inverse is also in H. Turns out if those two things are true, then H is a subgroup. I don't need this one and I don't need this one. Let's prove this. And as I say, that's why this gets exciting, because we're going to do proofs, and I'm going to show you actually just how easy it is. Because we have an if and only if statement, it goes both ways. You've got to prove, you've got to take this and prove this, and you're going to take this and prove that. Let's do it in what's sometimes called the forward direction. So I'm given that H is a subgroup. That's the easy part. So given that H is a subgroup, then by the definitions of a subgroup, which I've just given it to you, all four hold, meaning those two hold as well. Given that H is a subgroup, by the definition of a subgroup, you can write those two properties do hold. So it's proven in that direction. Now for the interesting one, let's prove it in this direction. Given that I do have this closure property, so I'm given that there is this closure property, can I prove then that given these two, what I'm trying basically to do is, given these two, can I prove that all four of them hold? Can I prove that all four of them hold? So I need to prove this associativity, and I need to prove that the unique element is also in H. Given just these two facts, can I do that? Well, let's say for all A, B, and C elements of H, given that because it is a subset, you can write out the words nicely, it implies that A, B, and C are also in G. Because H is a subset of G, and G is a group. We were told that it is a group. So because it's a group, A, B, C equals A, B, C. Because that is a group, so association holds. But that same ABC is also in here, so associativity holds for A. Huh. We were given this one, we were given that one. I just showed that this one is implied. Let's look at the other one. That the unique, I'm told that EV has its unique there. So for all A, element of H, it implies that A inverse is also in H. Because I'm given this. Does this help us make a group? Well, we've just been told, or let's just remember by definition, if I have A inverse in A, I get the identity element. I am given the fact that the closure property does hold. That means E must be in there. Therefore, that implies E is an element of H. So we also have that. So given just these two, all four of them are there. And that implies that H is a subgroup. I've proven it QED. I've proven it in both directions. So the proof is very, very easy. So now we know if we have this group G and if we take some of the elements out and we keep the binary operation the same, if we look at this new subset H and only these two properties hold, we know that that subset and its binary operation does form a subgroup, and the proof is very easy. I'm going to clean the board because it turns out this is not the only theorem that proves that if I have a subset and the same binary operation, not only this one, there's another way to look at it as well, which also will prove that will show to you that that is also a subgroup, and that's a different theorem. Let's clean the board and we'll do that one. So let's have a look at this theorem. It also says a non-empty subset H of group G. As you can again see, I'm using this notation of its subset and a G interchangeably because we're sticking to the same binary operation. Is a subgroup of G if and only if, so I've got to prove both ways, for all A, B, element of H, A inverse, binary operation B is an element of H. So first glance, this looks a bit different from the previous theorem, but it isn't actually, because what we are hiding there is the same, it is the same thing that we are hiding. So the proof in the forward direction again is very easy because I'm given the fact that this is a subgroup, therefore all the properties would hold, therefore these things would hold. And in reverse, what we're actually showing here is that A is an element of H and A inverse is an element of H. You know, that would imply that by the same way we did the previous proof, that E, the identity element, is also, and I needn't stick to A, B, and C, you know, A, B, that could have also been a C, so C inverse B would also be, so by the same token, I have A, B, and C in H, and therefore they are also part of A, B, and C, they're also part of G, and since it is a group, that means, since it is a group, it does mean that this associative property would hold, and it's going to equal A, B, C. So I'm just showing these other two. So it's just a different way of writing, but the same implications as the first theorem are in there in the statement that you have here as well. So the proof, other than putting the words out nicely so you sound like a mathematician, the concept of these proofs are actually quite easy. So let's just go on just to look at, and actually I hope you understood those two proofs. They are really, really simple if you think about it. Again, you are given some stuff. We have made definitions. Those definitions that we make, remember, they are, you know, that's what we come up with. We decide that as humans, that is our definition. And the tool set that we have in these definitions, we just use them and build new stuff. So we put a theorem out there, we prove a theorem, That's something new that goes in the box, and we can from now on just use that. We get that, it's a subgroup. Because we've already gone through all the steps of using prior definitions, prior things that we've put into our toolbox. Now this goes into the toolbox, both of these theorems, and we can just use them, and now we can use them in the next proof because we've already proven them. Let's look at some examples. Okay, so let's make my group G be A and a binary operation, and A is just going to be, remember, all the fourth roots of 1. And they were, remember, they were 1, so that equals minus 1 minus 1i, and minus I. Those were the 4. And if I were to have A prime only be 1 and minus 1, and my operation that I still have is still multiplication, and here it was multiplication for A, multiplication. Is that still? Now remember, I only have to show, let's use the second one. And so A equals 1. So A inverse, what is its inverse? It's also 1. And B equals minus 1. So A inverse with B, A inverse is 1 minus 1. 1 times minus 1, that equals 1. So lo and behold, this is, if I just took those two, that is a subgroup. Okay, let's do the following. Let's take the integers mod 4. The integers mod 4, remember those were just going to be my equivalence classes 0, 1, 2, and 3. Remember those? So if I were just to take, so that's my group. So or let's say my group is Z4 under addition. And my A is that. And let's make my A prime just going to be 0 and 2. And let's have a look at that. Let's see, let's do a Cayley's table of that. We have addition, we have 0 and 2, 0 and 2. A 0 and a 0 is 0, a 0 and a 2 is 2. 0 and 2 is 2, and 2 and 2 is 4, which brings us back to 0, which is there. So there we go, that's my Cayley's table. So all I said is I wanted closure, and is there closure? Yes, any of the two that I do, the solution is also part of the subset, so I have closure. And the other one that I want, everyone's inverse must be there. And so something must give me the identity element. And we know the identity element here is 0. If we look at this, we just look at this, we see the identity element is 0. So 0 is its own identity element, and 2 is its own identity element, because 2 plus 2 is 0. So I only needed those two. All the other two of my 4 properties hold by the theorem that we've stated. And so the fact that, I should just call this H, or so that is G. So if H was A prime under addition, it means H is a subgroup. Easy to show that that is a subgroup. So in short, that is subgroups. Very interesting stuff. And it gave us this opportunity to look at proofs, and just to show you how easy those proofs are. Never be afraid of proofs. Just do, as more that you do, the better you'll get at it. And it really is easy. And I don't think you'll forget the concept of those two proofs. They really are simple. Just what's in your toolbox, the properties that we have decided or the definitions that we've decided, that is what we would call a subgroup. Use that, what's in your toolbox, and the proof will come. And there's 2 beautiful examples of subgroups.